All right. Well, welcome back to Neutrino Day, everybody. We're so excited. We've had some great things already going on this morning. I don't know if you got to see Dr. Hugh Lippincott talk about dark matter, but if you didn't, make sure you get onto our website and watch it a little bit later. We don't want you to do that in place of other things today, but we want you to watch it later. Well, we've got a great thing coming up here today. I wonder if you have ever wondered, what if? Well, for science education experts Deb Wolf and Chad Ronish, they ask what if all the time. And it's just part of their job. That's just what they do. So right now you're going to experience some really weird science things. They're going to do some live demonstrations. Have a great time, and be sure to drop your questions into the different platforms so we can answer them for you. Thank you.
Hi, Chad.
Hi, Deb.
Here we are. So we are education specialists here at the Sanford Underground Research Facility in Leeds, South Dakota. And during our session today, we are going to practice one of the most important skills that scientists have. You know what that skill is, Chad?
Asking what if. What happens? What happens if I try this? What happens if I do this?
Yeah, practicing being curious. Practicing that skill of curiosity is absolutely essential for scientists. So what we're going to be doing today is talking about and asking questions, not just what if, but why,
How,
where, why did that happen, etc. And so although the title of our session is What If, I bet you're going to hear lots of different kinds of questions today.
One of the important things for you to think about at home is we want you asking your own questions as we go through this, because we're not the only ones with questions. Everyone has questions. So keep track of your own what ifs. What if we had tried this? What if they would have done that? Keep track of that as we go through the hour.
Yeah. And here's the other thing that I really want you to do both today and on into the future. I want you to slow down, and I want you to notice things. I want you to observe. So, for example, if you are going out on a hike, take that hike slowly. Look around. Look at the plants. Look at the animals. Look at the rock formations. And ask questions of the people you're with. And wonder about this planet that we live on, because that is going to prepare you for a job in science. It's going to prepare you to be good at whatever you do. So the other thing here at SURF that's super important, it's one of our core values, and that is
safety.
Safety, absolutely. So y'all will notice we both have on our safety goggles, our safety glasses. We're wearing lab coats that have longer sleeves. You can't see it, but we both have closed-toed shoes on. And eventually we'll put on gloves for some of our experiments. So we want to be thinking about safety in everything we do. And as you are doing your own what ifs, make sure to have an adult with you, somebody that you can count on and rely on to help you decide, is this safe, and what should we be doing that's safe?
Exactly.
And you know, these what ifs are all about thinking about scientific phenomena.
What's a phenomena?
Phenomena, do 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 do. Phenomena, do 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 do. Okay, so that was not in the script, but whatever.
It happens.
So a phenomena is something that we see or experience that we aren't really sure the answers to, that we can wonder about, that we can ask those what if questions. So for example, in our teaser video, we had the bicycle tire, the bicycle wheel, and we asked, what if? It was a phenomena.
Let me show them that.
Okay.
So this is us with our other science specialist, Ashley, and we've given her a bicycle wheel. and we spin it really fast, and that's what happens.
Well, that's kind of what happens.
That's kind of what happens.
Right.
That's kind of what happens. So, the bicycle wheel deals with forces.
Forces, yep.
Okay, so as we spin a bicycle wheel, we get something called torque, and torque is a type of force that happens.
Okay.
And so as you spin the bicycle wheel,
Yep.
the harder you spin it, the more force it applies, and the more torque it can apply, and that's what causes Ashley to spin around in a circle.
So like when she tipped it, then there was torque, and actually the torque caused her to spin?
And that's the best thing about it, right? So she tipped the wheel because she applied a force to it to tip it.
Yep.
And so then the wheel applies a force right back at her, and that's what's actually causing her to spin around.
Oh, very cool. You know, there are a lot of forces here at Surf.
A lot of forces. We deal with force with a lot of different things. Everything from our giant hoists that allow us to lower people all the way down into the lab, which is a mile underground and thousands of pounds, to tiny little particles like neutrinos and dark matter that are applying forces to other particles, and we can't even see them.
You mean there are forces on these teeny tiny particles, and yet they're super hard to detect?
There's lots of things like that that happen, and they're so small we can't see them, and we have to figure out, how can you see something that you can't really see?
How can you see something that you can't really see? You know, I was thinking about that, and I was actually thinking about soap. I was thinking about dish soap.
That's usually where I go when I think I can't see things. I go to soap, directly to soap. Yeah.
Well, you know, let's think about this for a second. Every time we wash dishes, we add soap to get things clean.
Yes.
Why?
I don't know why. It cleans dishes is all I know.
I know, but there must be something going on there that the soap is necessary for. And yet we can't really see it. So I have a way that we can see or detect the soap working.
Okay, I'm curious. You've got my curiosity piqued. Let's see it.
Oh, good curiosity. All right, so here's what I've got. I've got some whole milk. And all I'm going to do is I'm going to pour some whole milk into this pie tin, okay? And our milk is going to kind of act like our dirt,
Okay.
or the food particles that we need to scrub off our dishes. Now, we want to see the soap working when we add it, so we're going to add food coloring. And the only job of the food coloring is to act as our detector, to help us see the soap working.
Okay, so we're going to use food coloring to watch the soap work.
Yes.
Okay, cool.
Yes. All right. So 4 drops of food coloring. Let's do a blue, a green, red.
Okay, that looks really cool in the milk. How the food coloring just kind of makes a little puddle there.
Yeah, and mostly it's just sitting on the surface.
And it just sits there.
Yeah.
Just sits there. There doesn't even look like they're mixing.
For the most part, you're right. They're basically just sitting there. There's actually what's called surface tension, and the surface tension of the milk, because milk is mostly what?
Good. No, milk. There's fat.
Delicious.
There's water.
Yep.
A lot of water.
Yep, it's mostly water.
And then there's like fat and happy goodness. Okay, yeah. Okay,
Yes,
that's all
so
in milk. Okay,
I'm
good.
gonna your happy goodness.
Yeah.
Fat, because it's whole milk.
Okay.
And protein.
I like protein. Protein's good for you.
Yes. So now we have our food coloring sitting on the surface of our milk, and all we're going to do now is we're going to see if we can watch the soap do its thing.
Okay.
Okay? Are you ready? So I've just got a Q-tip here, and I'm going to dip the Q-tip right into the milk. Now I want you to watch. And cameraman, I'm just asking, are we looking down?
All right.
Excellent, thank you. All right, because this happens fairly quickly. Here we go. Everybody watching?
Wow. That is so cool.
Now remember how I said we're gonna slow down. It seemed like it happened really, really fast, but let's just kind of watch this for a moment and see if we notice some things. Chad, what kinds of things do you see happening?
Well, I see the food coloring moving to the side. So I guess my first thought would be is that the soap's pushing the food coloring away.
Oh, that's interesting. What else do you notice?
Notice that it's all collected around the side. Wait a sec. It's like it's making, there's more coming out right there where you've got in there. It's like making more and more food coloring there.
Well, it isn't making any more food coloring, but it is actually causing it to spin. So here's the thing. So, as you said a little bit ago, we talked about that milk has fat in it, and it's got protein in it. And water doesn't love to mix with greases and fat.
Exactly, right? So
Right.
if you take grease and you run water on it, it just runs right off the top.
Yeah, absolutely.
Yeah.
And so soap is an interesting molecule in that it sort of makes the water attract to the soap. And so what you saw happening is all of the molecules that were inside there, they have positive ends and negative ends, almost like magnets, and they were all just rearranging and realigning. And so what we saw, because of our detector, our food coloring detector, we saw all of those molecules realigning, rearranging, and pushing each other in different directions.
So the milk was moving. The food coloring just allowed us to watch the milk move.
Yeah, exactly.
Okay.
Exactly. And the milk is mostly water, so that's what we're seeing. So, you know what's cool about this? One of the things that's really cool about this is let's think about what we used. We used milk, food coloring, and soap.
dish soap.
Yeah. So, what if we used not whole milk, but 1%?
Or 2%. I always have the blue milk, 2% milk.
Skim milk, half and half, heavy cream. They all have different amounts of fat in them, right?
And that could change what happens here.
I don't know.
What if?
Yeah.
Yeah.
Could we not try some other kind of soap? Hand soap, laundry soap.
Hand sanitizer.
That's not soap.
Oh, well then it wouldn't work. But what if?
What if? So we could change this, and you all could do this at home and answer those questions. What if not whole milk, but skim milk? What would it do differently? So that's our first set of questions. What if?
So does this work like the same way, like if I have a dirty plate with grease on it and you put like soapy water on it to clean it?
Yeah, the phrase I always use with my chemistry students, and this isn't entirely true, but it makes sense a little bit. It makes the water wetter.
Makes the water wetter.
Yeah, it helps the water do its thing, right?
Yeah.
You know, the color changes were pretty cool, right?
Color changes are really
Yeah,
cool.
and I'm wondering if we could do some other kinds of color changes.
Well, sure.
Okay, so
sure. Let's try something.
Yeah, let's grab our next set of stuff.
We don't need the food coloring anymore.
Nope.
Okay, I'll get rid of that.
Nope. Now we have a whole new set of equipment.
All right, so what do you have here?
So what I've got here is I've got some household ammonia.
Okay, so that's like the stuff you'd clean a floor with.
Yep, absolutely.
Okay.
I've got some vinegar.
Vinegar, don't clean the floor with that. Vinegar just stinks is what it does.
Yeah.
Yeah.
We use it in cooking.
Yeah.
I've got some just plain old water.
Okay.
Okay. However, my favorite part of this is something called universal indicator.
Okay.
This is going to be our detector today. Okay?
All right.
So, Chad, have you ever heard of acids and bases?
Of course, who hasn't? So acids like eat metals and things like that. And bases, oh wait, I know this one. Bases are like what I play in my rock band.
Okay, that's one kind of base. That is not the kind of base that we're going to be talking about today. We're going to be talking about chemicals.
Okay.
And acids and bases are kind of the opposite of each other.
Okay.
You know how Goldilocks, not too hot, not too cold, just right?
Yep.
Okay, so there's something called the pH scale, which measures how acidic, how acidy,
Okay.
or all the way over here, how basic, totally opposite,
Okay, so what's right in the middle then?
neutral.
Neutral. Okay.
Yeah, and water is a perfect example of something that's neutral.
Okay.
It's not an acid, it's not a base. I don't exactly know why I'm doing this sort of thing, but you know. Okay, so here's our water.
Okay.
All right, I'm going to put some gloves on. So this one I'm going to handle, Chad.
All right.
I'm not going to make you put gloves on. And what we're going to do is we're going to use our detector, which is our universal indicator, to show that our water is neutral.
Okay.
Not an acid, not a base. So here's our universal indicator. And by the way, if you want a universal indicator at home, this is a chemical, but you can actually make a universal indicator out of cabbage juice. It's pretty darn easy.
Red cabbage.
Red cabbage.
Red cabbage
yes,
juice.
Red cabbage juice. You take some red cabbage, you put it in your blender, you add some water, you make a red cabbage smoothie. And the liquid is actually an indicator.
Cool.
All right, so here's my water. And I'm going to add my universal indicator.
Okay, so that turned green.
Yep, so this is nice and green.
And that's what you would expect because green is neutral.
Yep.
Not an acid, not a base.
Yep, in
Okay.
fact, would you give me one of your pieces of paper there
Yep.
that we already used? And you'll notice that it's pretty green,
It's
right?
really dark, yeah.
Yeah, it's a nice dark green. I'm actually going to pour that into this tube, okay?
Okay.
Now I'm going to pour it, and I'm hoping I'm not going to spill too much, but you know.
It's science.
All right. So actually, would you just hold
Okay.
right there, and I won't pour on you. So I'm going to fill the tube up. So this is just water and my universal indicator detector.
All right.
All right.
You can definitely see that it's green now.
Yeah, isn't that just, it's like really pretty color, right?
Very green.
Okay, so now what I'm going to do is, would you take the lid off of that?
Okay.
Take the lid off of that, or open it up.
Or take it off?
No, that's fine.
Which
That's
one?
fine.
I can take the lid off.
Yeah, take the lid off.
Take the lid off.
Thank you. Take the lid off.
There we go.
All right. Now I'm going to get a little bit of vinegar. And I will tell you, vinegar is a weak acid, so it's a little bit acidy. And I'm going to put some of that into my tube. And remember, the universal indicator is supposed to tell us if we have an acid or a base.
Okay.
So something should happen if we add an acid to our water.
Oh, wow. I can see it. It's
Check that out.
It's like red.
It is like red. It's not even like red, it is red.
That is very red.
All right, so now I'm going to put the stopper on this, and I'm going to flip it upside down. What do you think is going to happen? So I should say it this way. What if I
Flip it upside down?
All right, so here I go.
Oh, it's yellow right here.
Yeah.
So we still have red.
Red at the very bottom.
We've got green.
Uh-huh.
And we've got yellow in the middle.
Huh, that's kind of interesting. Hope I got the stopper on that. So now I'm going to take this stopper off. And what if we add a base to the other end? Do you think something's going to happen?
Well, I bet it changes color.
All right.
I bet it's not red. Oh, it's
What do you see?
like purple.
It's like purple.
It's very much like purple.
Yeah. So I'm going to put the stopper on. What do you think is going to happen if I flip this again?
I bet they try to move.
All right, let's check this out.
So it's blue and purple.
Can we see this? So what have we got? We've got purple down at one end. We've got green.
Oh,
What happened to this end?
the red went away.
Why do you think the red went away?
It's not an acid anymore.
Oh, it's certainly not as acidy, right?
As acidic, okay. Should we add more?
Add a little bit more acid. So we have the vinegar one. Let's add another little squirt.
And it turns red again.
Yeah, our red came back. All right. So Chad, would you move the vinegar and the ammonia out of the way? Let's put that piece of paper down on our underneath our beaker
Okay.
so we can see well. And now I'm going to pour this whole thing back into the original container.
You should tilt it one more time.
I should tilt it one more
Yeah,
time.
what if you tilt it one more time? I got to see it. That's
All
pretty
right.
cool.
Actually, we have a beautiful rainbow right now.
Yeah.
Check that out. Wait, tip it one more time. Yep, we have purple. You can see a little bit
Purple,
of blue.
blue, green, yellow,
A tiny bit of
orange, red.
Yeah. You know what we call this?
Roy G. Biv.
Well, yeah. I call this the pH rainbow tube.
Oh, very cool.
Yeah,
Very
yeah,
cool. It's like a rainbow.
It is. All right, now I'm going to pour this all back in there.
Okay.
And I wonder what color
It will be.
colors when we're all done. What do you guys think? What do you think is going to happen? Let's check this out. It's purple.
So there's the purple.
It's
So it's dark
purple.
blue.
Oh, it's
There goes the
blue.
green. There goes the yellow.
Is it going to go all the way to red?
There goes the red.
You know what color it's back to?
It's right back to green.
It's back to green. Because what do you suppose an acid mixed with a base makes?
Neutral.
Yeah, yeah. So we're back to neutral. All right, so that's our pH rainbow tube. And one of the things that we could see is that we used our indicator
Yep.
to see when we had an acid, when we had a base, and when it's neutral. You know, here at SURF, we test pH as well.
Oh, yeah, because we've got all kinds of water here down in the lab.
Yeah. Well, not in the lab.
Not in the lab, but
No.
underground. There's a
Right,
lot of water,
right.
yeah.
It infiltrates in, and then we have to pump it out, and then that water goes to...
The wastewater treatment plant. I've got a picture of that.
All right, awesome. Wastewater treatment plant. Love that place. And they want to make sure that the water that we put back into our environment that we pump from the underground is still, you know, it's safe and it's clean, and that the pH is
Neutral, yes.
And so that's one of the things that they're going to test. That's one of the things that they're going to test is the pH. All right. Are we ready for our next?
While you're doing your next one, we need to swap your battery out.
Oh,
We're going to swap batteries,
okay.
okay?
All right.
Sorry about that.
That's all right.
Well, I'm just going to push this to the side
Perfect.
for now. So, something else that we deal with all the time at the lab is temperature. We have an entire system devoted to something called cryogenics, and maybe you've heard about cryogenics. Cryogenics is when we cool things down to a really, really cold temperature for different reasons. You might have heard about, so Captain America in the Marvels crashes his plane buried in the ice. He's cryogenically frozen for 40 years, and then Captain America comes back. So that's cryogenics.
Yeah, that's not science.
That's
though.
not real science,
Yeah,
but it's
just
pretty
letting
cool.
you know that.
But we use cryogenics at the lab because we work with a lot of really exotic gases and liquids, and specifically we use gases that we need to turn into liquids so that we can use them in our detectors as we're looking for different particles. And so we like to cool things way down with different substances that can get us to really low temperatures. And so we brought something along today to work with, something called dry ice. Do you want to explain dry ice?
Ooh, dry ice, dry ice. So dry ice is one of my most favorite chemicals to work with. And dry ice is solid carbon dioxide. So everybody take a deep breath in. Hold it for a minute. I can't because I'm going to talk. And now exhale. That stuff, mostly that you're blowing out, is carbon dioxide. But it's carbon dioxide as a gas. And what Chad has here is not carbon dioxide as a gas. He has carbon dioxide
as a solid.
As a solid. And now you'll notice, Chad, these are some fancy gloves you got here.
They're clean too.
So why do you have these gloves on?
Dry ice is really, really cold. It's minus 109 degrees Fahrenheit. So
Wait. Minus 109.
109.
So the coldest I have ever experienced is like minus, I don't know, 20 or 30, right?
So this is a lot colder than
that. A lot colder than that. Now we actually, at SURF, we use liquid nitrogen.
Yep.
And this is minus 109. The liquid nitrogen is minus 330, I think. I think I'm right on that number, but darn close. So like many, many times colder even than this.
Yes, it's very cold. And we use that because if we can cool it, we can actually change the state. So you can see here with this dry ice, which is carbon dioxide, since it's so cold, it exists right here as a solid. Now we call it dry ice because it doesn't actually turn into a liquid when it goes from solid to vapor. It goes through a process called sublimation, and it just goes right from a solid to a vapor. And I don't know if you can get this good with the camera, but if you look in here, you can actually see the vapor forming around our ice cube. So our ice cube doesn't get wet.
So that's why they call it dry.
Dry ice.
Dry ice,
yeah.
because it's
like
really cold.
Yeah, it's like my humor.
Yeah.
It's a little dry.
Okay, so this is not ice. It's not solid water. It's solid carbon dioxide. And as it warms up, it doesn't melt, but rather turns directly into a gas.
Exactly.
Great, I got it.
And so you can see this fog that's in here inside of our glass. Wonder if it would be better if we put it on a piece of paper.
Okay.
I don't know if you can see it better or not. Or if we put a little air across it, you can see the vapor move. So it's like fog. And so what we're actually seeing there isn't the dry, or isn't the carbon dioxide, because carbon dioxide's an invisible gas. You can't see it.
See? You can't see mine.
You can't see it.
Yep.
But if you think about exhaling when it's really cold out, and you can see your breath, what's happening is the water vapor in the air does like to change from a gas to a liquid to a solid. And what we're seeing here is the really cold carbon dioxide gas minus 108 degrees Fahrenheit, because now it's a gas.
Oh, okay.
But the water vapor around it doesn't like that. It wants to be a solid at that point. So we're seeing ice crystals, water crystals, water drops forming in here, and that's what that fog is. So the fog is actually moisture.
Oh, hey, what if we took our dry ice and added more moisture?
I think we should try that.
Okay.
I think we should try that. Should we do it in this?
Yes, absolutely. So I'm gonna add some water. Maybe about halfway up.
I'll grab some tongs here.
Okay. You might need a smaller piece than that one to fit in.
Okay, I've got smaller.
Okay. So let's all...
Yeah, I can almost grab it with the tongs.
This is like There's like those games where you have to like
Got
grab.
30 seconds to grab a piece of dry ice.
Yeah. Ooh, and it's screaming.
I think we'll do it this way. Just
Wah,
gonna be innocent. Wah, wah, wah.
Okay. Our audience here is giggling at us.
Yeah.
I hope you know that. Okay, this is awesome. So I got to look down here. So here's my dry ice. And it looks like the dry ice is boiling.
It looks like it's boiling in there, but is it hot?
No, it's actually quite cold.
So it's not boiling like what we would understand boiling, but
Well,
there's
it's not like
definitely
water boiling.
but there's something bubbling there.
Well, it's the carbon dioxide. That's what you told me.
The carbon dioxide's boiling out of there. So you're seeing the carbon dioxide bubbles come up to here, and then as they get to the top, that's all the water that is
And the carbon dioxide.
and carbon dioxide that's
Right.
condensing into the fog.
This is super interesting though. Look at this. When the fog comes out, it's not like smoke. So like if smoke were coming out, it would be just going up and billowing around here, but it's like falling.
So what's going to cause something to fall? It's got to be heavy
So it's heavier than the
air that's around it. So what our mixture, our water vapor and carbon dioxide is heavier, and so it is falling down to the bottom, which is kind of cool.
that dry ice, kind of cool stuff.
Dry ice is a lot of fun. But
Yeah.
what
What if?
if we combined our dish soap with our bubbling dry ice? Because that's got water in it, and dish soap already does stuff. So I think we should try that. I think we should put
okay.
a couple drops of dish soap in our dry ice.
Just because I want us to be dramatic, I'm wondering if you would add one more piece of the dry ice to that.
I can be dramatic.
And then I'm going to
I have people that will tell you I can be dramatic.
okay, and then also I'm going to suggest
We put it on here.
that we put it on there. All right, in anticipation of whatever we don't know is going to happen. Yeah.
But if it happens, we'd like to be ready.
We're
yeah.
prepared. Okay,
Yeah.
so little dish soap in with our dry ice and water. Let's give it a little watch.
All right, so that's pretty cool. So we've got bubbles, just like you would think there, but the bubbles are filled with smoke, or fog in this case.
So this is just carbon. It's cool. It's not cold, but it's cool. Oh, but watch this. Watch this. Poo, poo. Yeah. So they're filled with carbon dioxide and the water vapor, right?
To give it that little foggy effect.
And they're also really heavy because they're just falling like crazy.
Yeah, they fill the tray up.
Can we just do this like all afternoon?
We can, but I think our audience would get really thin after a little while watching us play with soap bubbles.
Okay. Somewhere here I have paper towels. All right.
So those are little bubbles,
Yeah.
right?
Those are little bubbles. They're cute, but they're small.
Can we make bigger bubbles?
Huh. What if we tried?
What if we can try to make some bigger bubbles? Get a bigger container. Do we have a bigger container? Oh,
We do have a bigger container
I'm going to just move this guy
into the.
into our collection vessel.
Okay. All right, so there's a bigger container.
So this is just an ice cream bucket,
Yep.
and that's got water in it.
Yep.
So I'm assuming we're going to need to add some dry ice.
If we want the cool, foggy, smoky filled bubbles,
Okay, so here's dry ice in there.
we should just stop right now because that's fun.
That's pretty cool right there.
However,
If we had spooky music, we could like do a scary movie scene right now.
we totally. I wonder if this is how they do scary movie scenes.
Magic tricks.
Yeah. Okay, so I made my own homemade bubble solution. And I made my own homemade bubble solution because I'm going to say it's a little bit stronger.
Okay.
And so what I did is I took some Dawn dish soap,
Okay.
mixed it with some water, and then I actually added a little bit of corn syrup. and stirred that up. So it just gives us a little bit better bubbles.
All right.
All right, and so now I just have a piece of folded paper towel, and it's been dipped in the soap, and this may take a couple of tries, but let's see what we can do here. Or I might be able to do it on the very first try.
Wow, look at that.
That's a big bubble.
That's a big bubble.
I wonder how big the bubble's going to get. Will the bubble break?
How big?
How big a bubble can we?
How big a bubble can? That's really cool. So.
Oh yeah. Let's do that again.
So that like just fell off.
It did. It totally just fell off.
But again, that makes sense, right? Because it's heavy.
And
so it should fall.
Yeah, it was heavy and then it got like lopsided and
Yes.
fell. Yeah. Should we do this again?
I'd do it again.
Okay. 2 in a row.
Okay, that's pretty good.
All right. So
What happens if you touch? Because we could we scoop all the bubbles
you
coming
got
out
to
of our
talk fast. This
cylinder.
is going to get big.
So what happens if you touch it?
Well,
Oh.
I broke the bubble. Yep.
So that's pretty cool.
Yeah, that was cool. However,
What if your hand's wet or your finger's wet?
well,
What would happen?
it's pretty wet. Well, I can make it a little. There we go. All right. Let's see if I can.
Oh, wow.
Check. Did you see that?
That was pretty good.
Yeah.
That was pretty good.
Okay, so why would that happen?
Why would your finger be able to go in there wet but not dry?
Right.
It's got to be something with water.
Yeah. And the soap bubble, there's actually water trapped in that bubble. And it pops when it dries. So if my finger is dry, boom, it's all over. But if my finger is wet, oftentimes I can actually make it pass through. Should we do it one more time?
Very cool. Yeah, we should do that again.
Okay. So one more bubble. Wet finger. And it actually will go right into the bubble. And I can actually move my finger around
Without tearing
in
the bubble.
the bubble.
That is so cool. And then can you pull your finger out without breaking the bubble?
Yes.
Oh. But now it's going to tip over.
There we go.
And it tipped over.
All right. So that's pretty good.
Okay.
That's pretty good. I'm a fan of dry ice. I'm not going to lie.
Dry ice is good.
Now, before we move on, though, I do want to say one thing about dry ice.
Okay.
Right? It is super cold.
Super cold.
And so you've been the only one handling it.
Got gloves on.
Got your gloves on. And your parents can purchase dry ice.
Yep.
But this would be absolutely an activity you would not do without adult supervision. So dry ice, we got to be careful with it. We got to be careful with everything, but certainly that.
But in the hot summertime, like with that kiddie pool in the backyard,
No.
and a little dry ice in there to keep your feet cool.
Oh, but you know what? Could you make a giant bubble out of a kiddie pool?
That would be huge.
What if?
What if?
You guys should try it and then send us pictures.
Yeah, send
pictures.
pictures.
We would be impressed. All right. Chad, where are we going next?
I think we need to do some more bubbles.
Oh, okay. Yeah.
So, again, how big of a bubble can we make, right?
Well, we made a big bubble.
Big one there.
Yeah.
So we've got this device here that we can make bubbles with. We're going to bring this over to the table,
Okay.
kind of.
Okay, now if we want to turn it over here so we can
Let 'em
watch the
drop.
bubbles,
Okay.
right?
So, got a container. Well, let's put some water in this and some dry ice, and we're going to start making our fog mixture.
Okay.
And we're not going to put dish soap in this, though. We're going to
No.
put dish soap somewhere else.
Yeah.
Okay,
So just put your dry ice. You might need a little bit more dry ice. Put some water in there. So what Chad has is actually he has parts of 2 2-liter pop bottles. It's not one that's been cut. It's actually parts of 2 of them. He's added some warm water. And now he's going to add some dry ice.
we'll add that piece.
Oh yeah, that's going pretty good.
So it's like a fountain of dry ice.
It is a fountain of dry ice.
Yeah, it's not like it actually is one.
Yeah.
Okay, so I'm going to put this fountain of dry ice in this pipe.
Hey Chad, check this out.
There we go.
Okay, so that's cool in and of itself.
Okay.
Okay, but I was thinking maybe I would try to make bubbles.
Okay, let's make bubbles.
All right, let's see what happens here.
Oh, that's really cool. Can you see those when they hit the ground?
No.
I can see them when they hit the ground.
So we think it's cool. All right, here's a question. Can you catch a bubble?
Well, I was able to handle them before.
Oh.
It just breaks.
Yeah.
Wait a second.
Yes.
What if I get my hand wet? Because you said that bubble's made of water.
Oh. So if you get your hand wet, let's make some more bubbles here. Oh, nice job.
Now I have a bubble in my hand.
What are you going to do with it?
I'm going to poke it. What have you done?
Well, I don't know why.
Seems like a silly question now when you think about it. Try this again.
Okay.
So I can blow on it. I blew way too hard.
But once again, one of the things that I notice is how fast those bubbles are falling.
Exactly. They fall, they're very heavy.
Yeah.
Well, I mean, they're not like heavy, but they're a lot heavier than the air.
Well, they probably seem extra light to you because I know you've been working out a bunch.
I know, I do. Yeah. I work out. So the big question is,
Yep.
when they hit the ground,
Yep.
what's on the ground down there?
Well,
I mean,
it's
there's
carpet.
nothing. It's absolutely clean.
Yep.
So because the dry ice, it's dry.
Oh yeah, there's nothing there.
There's very little water with that. It's
Right.
mostly the dry ice.
Okay, awesome. Well, it looks like we're about done with the dry ice.
Okay.
Okay. What are we moving on to?
You know, we did the soap thing with the dry ice.
Yeah.
But we haven't done the pH thing with the dry ice.
The pH thing with the dry ice.
That indicator, that rainbow tube you made.
Oh, so we could determine whether or not the dry ice, the carbon dioxide, would turn the water into an acid or into a base.
Or do anything with it.
Or do anything. So what if we brought this guy back?
It's like working in a mad scientist lab. But unfortunately, that makes us the mad scientists.
Okay. Okay. So this was our original water.
Yep.
And it is neutral right now.
Yep.
Because it is
green.
Green.
Green says neutral.
Okay.
Yep.
And so if we add some solid carbon dioxide, some dry ice to our color, or to our neutral water, will it do anything?
Well, it
And you
bubbles.
added so much.
Perfect. Just blow.
Oh yeah, blow the cup.
Oh wow, it turned it yellow.
To me, that's orange.
Oh, that orange, I'll go orange. It's orange.
So it's definitely orange right now, and it's almost moving to like orangey red.
Almost red. So that would indicate to me, based upon our rainbow tube,
Based upon our rainbow tube.
that's an acid.
That is an acid. So that's carbon dioxide
In water.
And all it did was just go into the water and it turns back into CO2 gas, right?
Right.
However, it must have done something to the water.
So if we mix carbon dioxide and water,
You know what? We get something called carbonic acid. Yeah. And not only that, and we would not do this because we would never taste a chemical, but that right there is going to be bubbly. Like it's going to taste like bubbly water.
It's soda pop. It's soda water. That's what's in there. Carbonated water, right?
Carbonated water.
The bubbles in soda pop, which, right? You open a container and it blows up on you. That's the carbon dioxide getting released from carbonic acid inside your water, inside your liquid.
So, can you buy an indicator, like somewhere, to test pH, like a household?
You can. If you go to like a hardware store, or if you've got a pool or spa, any of those kind of stores, they have pH strips.
Oh.
And you could take a pH strip and you put it into a solution, you pull it out, and it's going to change color, just like our indicator did. And then you can tell if something's acidic or basic or neutral.
So we could test things like ketchup,
Orange juice,
soda, pop,
milk, water. You could test
coffee,
anything. Coffee.
tea. Yeah.
Anything that you could eat or drink, or have around the house, you could test to see if it is acidic, basic, or neutral using test strips, just like we did. Or they could make that red cabbage solution, then run around with red cabbage slushies testing pH at everybody's house. Yeah.
All right.
Make you hit with the neighbors.
Okay. So I'm going to tell you this. We are down to 14 minutes.
Okay.
And so just kind of giving you a heads up on that.
Okay.
I think we're done with the dry ice stuff.
Yep.
And I'm going to let you transition to the next thing.
Okay. So we're using colors to see things that we can't see. We use indicators, so they allow us to visualize what's happening inside our science and our models. But you know, there's sometimes we don't even have to add things to it because the color's already there.
Oh, the color's already there. Where are you going, Chad?
I'm going over here.
Okay.
If you've ever seen fireworks.
I saw them on the 4th of July over the open cut.
And here's some pictures of fireworks, 4th of July, over the open cut. Fireworks have color.
Yes.
They get their color from the chemicals that are inside them. And in fact, all chemicals have some kind of color to them. If we get them excited and we allow them to release the light that's going to come from them, that's how we get all these colors.
If we get the chemicals excited.
You got to get them excited. Got to get them excited.
Okay.
So I'm going to set up a little experiment over here, try to anyway, where we are going to look at some excited chemicals. So this is just the camera from my laptop. And what I have right here is just a light bulb. It's going to get really bright for a second. That's just a white light. Same kind of light bulb you would have in your house. And what I'm going to do is I'm going to put a filter, a little piece of screen over top of my camera lens. And when I do that, you'll see that there are rainbows appearing on my camera. Seeing that pretty good? Looks good? Good. So, I don't know what I'm just missing. All right. You got to keep the camera open. So, what that is, that screen is taking all the light that's coming, and it's separating it out into the colors or wavelengths of light that make up this light. So, this light bulb is white light, and when we put our filter over top of it, it gives us all the colors.
Roy G. Biv.
Roy G. Biv. It's like a rainbow. But not everything is going to give us the full Roy G. Biv spectrum. So I've got some tubes here that have some different gases in them that we're going to look at. This first tube has helium gas, or hydrogen gas in it. So this is just straight, pure hydrogen gas. If you look at it, it kind of looks, purplish. This is what I mean by exciting it. Okay, because I'm running electricity through it.
Oh, so you had excited it with electricity.
With electricity.
With energy.
Gave it some energy, right? So then if I take my filter and put it over top, on the side there you can see the color spectrum that comes from it.
But But it's not a rainbow.
It's not a full rainbow. There's a lot of the colors in there, but it's got some are more prominent than others. And that's because different elements give off different wavelengths of light, and our filters allow us to separate those out. The better our filter, we actually call it a spectrometer, the better our spectrometer, the more we can separate them, but just this little film does a pretty good job of it. Let's look at another one. Let's look at helium real quick. So this is helium gas. It looks like it's almost, peach. I'm going to call it peach. And again, if we look at the spectrum from it there, that one you can see pretty good. You can see that there's definitely a little bit of red, a whole bunch of yellow, some green, and some purple there. But each one of them looks like its own little tube there, and that's getting separated out by the filter.
So essentially, Chad, we can identify elements or chemicals using the light that they give off?
Exactly, and that's exactly what we do, is we use this property to look at things that are a long ways away, like stars, and we can look at the light coming from them, and we can separate that to identify what types of chemicals are inside those stars. This one is neon.
Neon is pretty.
There you can see that it's showing a whole lot, all at the same wavelength, right there around the orange, and that's kind of what the neon spectrum looks like as you look at the screen. Here's one more. This one's really important. We want to show this one. This one is xenon gas. Xenon gas is a pretty important gas for us here at Sanford Lab because we use it in one of our detectors, Deb.
Yes, we do. In the Lux Zeppelin experiment.
You can see it has a spectrum there, and we could analyze that spectrum to figure out what it is. But it is just a gas, and so we actually take this one and we use cryogenics to freeze it down to a really, really cold temperature and turn it into a liquid. And then we use it inside the Lux Zeppelin detector to look for dark matter.
It's pretty awesome.
I've got a picture of...
Do you? Oh, awesome.
Here's a picture of Lux Zeppelin, and this is actually the first one. This was the first Lux detector, the first experiment. But inside that container would be liquid xenon, and that's where we're doing all the science, inside there.
So that's, that xenon, I'm going to use an analogy here, going all the way back to the beginning, is kind of like our food coloring in that it helps us see things that we don't otherwise aren't otherwise able to see.
Exactly. And what we do is we've got cameras in there, and so if a dark matter particle would hit it, the idea is that we would see something happen in the xenon, and any little bits of light or energy that came from it, the detector would record, and that's how you look for dark matter. Is they're waiting for a collision with xenon gas in the liquid form.
Yeah. I'm just going to say, I think it's more complicated than just that.
Well, that's just my understanding of it. There's some really smart folks down there. So,
I see Connie over there. Is she going to cut us off, or we have one more?
One more.
Awesome. So she's just setting up. So here's the last one.
Okay.
So this time I'm actually going to use a hard-boiled egg as our detector.
So a hard-boiled egg is a detector. And what's it going to detect?
Yep, it's going to detect air pressure.
Okay, we use air all the time here, right?
Yep.
Because we've got to keep that whole underground facility a mile deep.
Well ventilated.
Well ventilated.
Yep.
So we need to know how air and air pressure works.
Absolutely, absolutely. But I'm going to do something pretty simple, pretty straightforward, and just show everyone really how incredibly strong air pressure is. It doesn't feel like it, because it's not like the air in the room is feeling like it's doing anything to me.
Yeah, I'm good.
I could do jumping jacks, but I am not gonna. Okay, all right. So here is my hard-boiled egg. I've peeled it, and all I have is just this is called an Erlenmeyer flask.
Okay.
A glass flask. And if you were going to do this one at home, you would just want to have a container that your egg could sit on without actually falling into your container.
Okay.
So this, what we want to do now is we're going to work to alter air pressure.
Okay.
So we can't, it would be hard to alter the air pressure in the room.
Okay.
Okay. So what I'm going to do is I'm going to actually alter the air pressure inside the flask. And the way I'm going to do that is I'm going to lower the air pressure inside the flask by using up some of the air in the flask.
You don't think we could just like use neutrinos and push that egg in there?
Well,
Just like let the neutrinos keep hitting it and pushing it down?
doesn't seem to be working, even though there are millions of them going through the egg as we speak.
So there's like millions of neutrinos going right through the egg, and they're not pushing it.
It does not appear so.
Okay.
Okay, all right. So instead, I think I'll go with air pressure.
Let's go with air pressure.
All right. So to do this, and this would be another one of those where adult supervision for sure, I'm just going to take a little piece of paper towel and a tong. I'm going to give you the egg.
Okay.
And remember, we're going to drop it in
Pointy end down.
Pointy end down,
Pointy
yes.
end down.
So I am going to light this little piece of paper on fire. And so we're going to have a combustion reaction happen inside there. We're going to have a little tiny fire
So I'm going to hold paper
inside.
for you?
Yeah, that'd be awesome. You got it?
I got it.
Okay. Can you do all this?
We'll find out.
All right, here we go.
What if we give Chad too many things to do at once? That's the question.
Okay.
Is that good?
Yep. Put that in there and put your egg on.
All right, so that's
The egg's in the flask. So all I'm going to do is say this.
Okay.
Because we're out of time, Chad.
okay.
What if
What if
I wanted to get that egg back out of the flask without breaking the egg or the flask?
Well, I don't know. That's a great challenge.
Yeah.
That's a great challenge for all of them.
I think it is. So we're going to leave it at that. Don't just Google it, everybody. That's too easy. Think about the fact that I said we had to change the air pressure. All right. That is all from us.
Keep asking what if. What if is important. Why is it happening? Think about science. Think about the world around you. Starting to think like a scientist is the first step to becoming one.
Yeah, be curious.
Be curious.
Well, wow, Deb and Chad, holy cow. Not only was this very informative, it was fun.
Well, thanks.
I mean, who knew that science could be so fun? I'm going to answer that myself. Scientists and Deb and Chad, obviously, because they made this one of the, just a great experience for us. Thank you so much, everybody. Let's applaud. I mean, in Gathertown, applaud this. This is awesome. All right. Well, thank you again. That was just perfect. So I want to thank you all for attending this. Now, we've got one last special event coming up today, and that is Dr. Lee, who is going to talk to us about Lakota, Dakota, Indigenous astronomy, and the practice of combining perspectives to better understand all of the things around us. So don't forget to join us at 4 o'clock Mountain Time. And in the meantime, there's still lots of fun stuff to do in Gathertown. So keep playing around in there and keep on learning, because it's fun to learn science. So thank you all so much, and we'll see you in a little while.